Let's get going. Thank you all for logging in and spending your lunch hour with us today to learn more about how nuclear power works. Today actually marks the fifth and final session in our online learning series that included a lot of different conversations. We talked about how our power is changing, how it moves, grid modernization and small scale technology, and why we're even thinking about nuclear power in the province today. So we're going to continue that conversation about nuclear with today's session and get into how it works specifically. My name is Alexis Doyle. I work for SaskPower as a public engagement consultant. And joining me for today's session is Osama Beg, who is the innovation lead at Ontario Power Generation, Centre for Canadian Nuclear Sustainability, and Steve Livingstone, who is the small modular reactor specialist with the Crown Investment Corporation here in the province, and formerly with the small modular reactor unit at the Ministry of Environment, where he also was the SMR specialist for the province. So both of you have extensive experience in the nuclear industry, and I've really appreciated how both of you make complex ideas simple. So when it comes to nuclear, which can get very complicated really quickly, I'm very thankful that both of you are here today for this chat. Now, I'm familiar with your backgrounds, but I wonder if each of you could just take a quick minute to share more about yourselves to those who are listening in. So Osama, would you like to start?
Sure. My name is Osama, background in nuclear engineering, and involved here at Ontario Power Generation, which is largest utility here in Ontario. We own 19 operating nuclear reactors, and in my free time, I actually create videos on my YouTube channel that demystify and simplify nuclear technology. So something that I do in my free time as well. So yeah, that's me. Thanks.
Thanks, Osama. And Steve.
Yeah, and Steve here. Yeah, so I've been here 2 years, but before that, I spent 14 years at Chalk River Labs in Ontario, studying all kinds of things related to SMRs and nuclear fuel and big reactors and small reactors and some nuclear waste stuff. And yeah, I've been bringing that expertise here, and I've also been doing a bit of a Nuclear 101 presentation a few times in the province. And yeah, kind of a complicated way to boil water that we'll be talking about today.
Perfect. Thanks, Steve. Yeah, I'm excited to get going and having this chat with both of you. And if you can take a look at the chat, we actually just put a link to Osama's YouTube videos for you to watch in his channel there, for you to learn more. That's actually how I became familiar with Osama first, and then only realized later that he was a counterpart at Ontario Power Generation. So excited to have you here joining us today. So before we get started, I just want to acknowledge that the work we do here at SaskPower reaches the ancestral lands of many nations in the province, including those nations on Treaty 2, 4, 5, 6, 8, and 10 territories, as well as the Dakota and Métis nations. And Steve and I are actually speaking to you today from Regina, which is located on Treaty 4 territory and home of the Métis. And just on a personal note, I just wanted to share that earlier this month on Remembrance Day, I wore a beaded poppy that was actually made by a woman from Pheasant Rump First Nation. And I was in Pheasant Rump this summer, and I attended their first powwow since COVID and my first powwow ever, which was sponsored by SaskPower. And it was a really beautiful celebration with community members and surrounding and visiting First Nations. So while I was visiting their community, I actually learned more about their veterans and their community. And so wearing the poppy brought new meaning for me for November 11th this year. And it was actually an opportunity to share more about my experience with others that would comment or ask about the pendant. So I just thought I would share that piece. Osama, I know you are joining us from outside of Saskatchewan. So where are you calling in from?
I'm calling in from Mississauga, but OPG sites, the CCNS, Center for Canadian Nuclear Sustainability, where I work, is located traditional treaty territories of the Michi-Sagi and the Chippewa Nations, and also the Durham region and surrounding areas, which are home to Indigenous peoples and territories from across the country. So that's basically where I'm calling it from.
Great. Thank you. And thanks again for making the time. I know the time difference is a little bit different. So it's not your lunch hour, but thanks again for making the time to be a part of today's conversation. Just a few technical notes to get out of the way to start. and some more information on how you can submit issues when it comes to technical difficulties. At the bottom of your screen, you'll see a black banner that includes a chat function. And when you click on it, it will open a new pop-up box. And here you can send messages directly to our technical support, which are sitting in the background and are available if you are experiencing those technical issues. So use the chat function to communicate those challenges. And then when it comes to asking the questions, which is what we're here to do today, you want to click on the Q&A box at the bottom. And that, again, will pop up a new box, and make sure you enter your question and you do click send. And these questions should only be seen by us if we've set it up correctly. Sometimes we miss that box when we're taking up the Zoom or setting up the Zoom meeting. But hopefully we'll only be able to see those questions. So there's no wrong question to ask, and no dumb questions when it comes to nuclear. And so we will reply to your question either in writing or during the session today. Because this is more of a dialogue and a discussion, what we'll do is try to work in your questions throughout today's conversation and hour-long session today. So that's a little bit about the housekeeping. But I thought we could start off by sharing a short little video of our SMR project here in Saskatchewan. So hopefully this all works tickety-boo.
At SaskPower, we're focused on our goal to reduce greenhouse gas emissions. That's why we're pursuing many non-emitting solutions, each with pros and cons that we evaluate. One option is nuclear power from small modular reactors. Did you know nuclear produces zero emissions?
Sorry?
Like larger traditional reactors, they use nuclear fission to generate heat. Nuclear fission is a reaction where a uranium atom absorbs an extra neutron. This splits the atom, which releases energy. The energy is used to heat water, which makes steam to generate electricity. These new reactors are much smaller than those used in Canada today and have enhanced safety features. Many parts are built in factories and assembled on site. This helps reduce costs and improve quality. The nuclear power industry is highly regulated. If we want nuclear to be an option in the future, we need to plan now. We're looking at all options that provide a clean, safe, and reliable future. Visit saskpower.com/nuclear for more information.
Okay.
At SaskPower,
So that was a short 1-minute video, probably the quickest overview of the nuclear industry, right? Would you agree, Stephen Osama?
That's right. That's right.
Yeah.
Good summary.
Yeah, it's a good summary. So let's maybe take a quick step back here. Steve, maybe I'll look to you. Could you just describe again how nuclear power or how nuclear reaction works? And maybe what is the same or different when we compare it to other options, say like thermal generation options like natural gas, for example?
Yeah, and that goes a bit back to my quote about complicated way to boil water. And yeah, I assume everyone can see your little slide with the kettle.
I hope so.
Heat.
I hope so.
Okay, good.
Yeah.
I can. Yeah. So when it comes to coal, gas, or biomass, those are also thermal plants. And so they burn those materials to make heat, like we see in this little picture here. And then you use that heat to boil water to make high pressure and high temperature steam. And then if you push that steam into a turbine, it'll spin the turbine, and that will spin a generator, and then that's what makes the electricity that we see on the grid today. And so those aspects are the same for all these different thermal power plants. And so for a nuclear plant, you're just using that nuclear fission to generate that heat, but then you're still using that heat to boil water, to turn a turbine, to turn a generator, to make electricity. And so the thermal power plants are very similar in those aspects. We shall sometimes see called the balance of plant is one of the terms that's sometimes used for that.
Right. And so maybe more specifically about that fission concept, what happens in the reactor? Like how exactly does it make the steam?
Yeah. And I think we saw that with the atom splitting in two, which is what they call fission. And actually, anyway, for me, one of the cool things I think about with nuclear power, so I'm assuming people have come across the equation E equals mc squared, fairly famous equation from Einstein. And that's actually where the power is coming from in a nuclear reactor, in that when that atom splits, a small amount of mass is actually converted into energy. And that's the energy that we're then using to heat the water to make the steam. And so that fission reaction causes that ever so slight conversion of mass to energy, and then we use that energy to provide the heat. And so it's different to coal, gas, and biomass. Those are chemical reactions, which doesn't generate as much energy, let's say, for the amount of mass you're burning, which I think will come up later.
Yeah, interesting. And so when just more on that, like the atom splits, and then what happens to those atoms? What do they go on to?
Yeah, that's right. It's a great question. So it splits and it releases some neutrons. And so the way a reactor works is to use those neutrons to split more atoms. And so if you can get everything arranged just correctly, you get a nice balance of you making as many neutrons as you are using to split the fuel to make fission. And then those other fission products are what we find in the radioactive spent fuel. And so that's part of the waste from the fission process. And so then we store and manage those. And I believe we talk about that later in the slides.
Yeah, actually not a bad segue. I don't know, Osama, if there's anything you want to add to that description of a simplified version of nuclear fission.
Yeah, I think that was honestly a great overview, Steve. Yeah, nuclear fission, the chain reaction, which is kind of controlled in a nuclear reactor. So reactor does a really good job in safely controlling that reaction of nuclear fission. Yeah, I guess maybe later on in the presentation we'll kind of go through that process as well. And kind of, yeah. So not much to add.
Okay, no problem.
And you could, that's right, you could get a doctorate in that process, but that's right. It's just a very simplistic.
No, that's important.
At a basic level, that's how it works. Yeah.
Yeah. No, I think that was a good way to describe it. And I hope that was helpful for those listening in. And so you talked a little bit about waste, Steve, and maybe let's talk a little bit more about waste because, or the fuel.
Right.
So with the power input or fuel in mind, can you tell me a little bit more about the energy density of uranium? We always talk about energy density in the work we do. And how does that, again, that idea of comparing to other power generations like natural gas or coal, can it help kind of us appreciate the intensity?
Yeah, that's right. That's often a question that comes up, and it's hard to, even for me working in the nuclear space, hard to get my head around how energy dense nuclear is. And so my one little example that I did, because I was kind of curious myself, I actually looked at my SaskPower electricity bill, because we all use SaskPower in Saskatchewan. And I looked at my house in Regina and my bill, and I was trying to think about, what kind of nuclear waste would be generated to power my specific house. And so I did go through the math, and if I was to get a kilo of fuel, which you could hold in your hand, it's not a particularly large amount, and I was to give that to SaskPower or OPG, and they had built one of those GE-Hitachi reactors, then that 1 kilo of nuclear fuel in the reactor could power my house in Regina for 99 years, which is a significant amount of energy and a very small amount of fuel. And then it's also 1 kilo minus an absolutely tiny amount of mass that was converted to energy that would be the waste. And to compare that against coal, if I was to drive to one of SaskPower's coal plants and give them a kilo of coal to put into their boiler to make electricity, then that would power my house for about 4.5 hours. And so I hope that gives some kind of sense of the energy density difference, and also talks about that there isn't a huge amount of waste associated with nuclear power because the energy density is so high.
Right. Yeah, and I think this graphic here gives them a few other ideas in terms of comparisons, right? So we have this uranium pellet here, which is the black sort of cylinder, and it's about the size of a gummy bear and the weight of a AA battery. And if you had 10 of these, same idea, right? If you had 10 of these little pellets, it could power an average Canadian household for about a year. And recently I was sort of describing how, like, what a fuel bundle looks like for for OPG or our existing reactors, where you take all these little pellets and you kind of stack them. This is, again, a simplified way to describe it, but you stack them into like a fuel rod, on top of one another into a rod, and then those rods get sort of coupled together into a bundle. It's about I think it's 50 pounds, right, Osama, a CANDU bundle? Yeah. So that's what it looks like when it goes into our reactors today. And so thinking about our fuel and where it comes from, what is the current fuel supply chain process for the nuclear industry in Canada today? And Osama, working at OPG, I was hoping you might be able to share more about that.
Sure. Yeah, I can give a high level overview. So luckily in Canada, Canada has some of the highest quality of uranium ores anywhere across the world. So, the uranium, most of our uranium, all this is mined and milled in northern Saskatchewan. So, many of you on this that are listening in, you might be located there, but it's located in the Athabasca Basin region, and the ore is basically mined. It's sent off to refinement facilities, okay, where it's milled. So this is located in Blind River in Ontario, okay. Then you basically take that refined uranium, and it's transported to a facility in Port Hope. So here in Ontario, we do have a facility run by Camco where they convert this natural uranium powder into pellets, right? So the pellets that you see on the screen, right? So these pellets are then, like Alexis explained, inserted into uranium bundles. So fuel bundles, which are basically made out of a metal called zirconium. They're around the size of a wooden log, so like this big. And they're super energy dense. They're easily transported to nuclear facilities. That's kind of like an overview of the process.
Okay, and how it moves in Canada today, I think it's all transported by truck, right? On highways, how it moves through that process. Yeah. Steve, any thoughts on that?
And then, well, just for myself, I did get to go to Key Lake Mill last summer. It was very neat to see an actual uranium mine. That's right. I've worked in That's right. Worked in the uranium industry for 14 years, never been to where the actual uranium comes from. So it was neat to actually go see an actual facility where they are mining and extracting uranium, as Osama was talking about. And then there is one other piece. So he described how it works for the CANDU reactors in Canada today, where that fuel will, it gets processed, fairly simple processes, and then ends up in the reactor. But for the small modular reactors, they'll be looking to use enriched fuel, which is not something we do in Canada. And so on that facility in Ontario, instead of converting the uranium into that little pellet that we see in the picture, they actually convert it into a gas called UF6 gas. And then that gets exported to either the US or Europe, where it then gets enriched. And then they convert that gas back into pellets, just like this gummy bear, but now it's an enriched uranium. And that's what would go in one of the 400 reactors around the world, or going forwards into the SMRs in Canada.
When you talk about enrichment, can you just explain what that term means?
Yeah. So hopefully folks remember their high school physics or chemistry classes.
Maybe not everybody took. Not everybody took those classes. Maybe not.
Steve.
That's right.
That's right. So the uranium that you find in the Athabasca Basin, if you were to go dig some up, and hold it, 0.7% of it is this thing called uranium-235, and 99% of it is a different isotope called uranium-238. So they're both uranium atoms, but they have different numbers of neutrons. And that's incredibly important when it comes to the fission process that we were talking about. And so when those atoms split and release that energy, it's the uranium-235 that is doing that process. And that is only 0.7% of the little pellet that you see on the screen there. And so the CANDU reactors are designed to be incredibly efficient machines. And so they can operate on that natural uranium, even though it's only 0.7% of that pellet is uranium-235. that's enough for a CANDU because it's so efficient with it. But then you have to do other things to make that happen. And so the SMRs enrich the fuel, which means increasing the amount of uranium-235. And so, for example, the reactor that SaskPower is considering, the BWR X300, it needs, I think, about 4 or 5% enriched. And so that uranium, you need to increase the amount of uranium-235 up to about 4 or 5% of the total uranium. And so those little pellets will be about 4 to 5% uranium-235. And then that allows you to come up with some of these cool features that you see in the SMRs because of that enrichment. But it adds that extra step, which we haven't done in Canada before because our CANDU reactors don't require it.
Okay. Yeah. And why would we have to ship it to the States for it to be enriched?
Yeah, that's right. That's a great question. And yeah, it's historical that because our CANDU reactors don't need enriched uranium, we've never had a requirement to enrich fuel in Canada. Whereas all the other countries that are running what we call light water reactors, and there's 400-ish of them, they pretty much all operate on enriched fuel. And so all those various countries have developed that enrichment capability. And it's a fairly complicated process and expensive to set up. And so considering we didn't use enriched fuel, we never built that capacity in Canada today. And so the first SMRs will have to procure that enriched fuel from somewhere else, although the uranium itself will most likely come from Saskatchewan. We are the second largest producer in the world of uranium.
Interesting. Okay.
Yeah.
Okay. For folks, if you guys have questions, as both Steve and Osama are sharing more information, please submit those. And so thinking about where you might put an SMR, where nuclear power is sited here. So in September here at SaskPower, we announced 2 potential study areas here in the province of where we might site our small modular reactor. And we narrowed down to these 2 areas based on a list of criteria. And one of those was the need for a large water body. So I know this is a question that comes up often when I'm out in the public and talking with folks about this project. But Osama, I wonder if you could share a little bit more about why we need water for a nuclear power plant. Like where does the water go? How does it move through the facility? Does it touch the reactor? These are the types of questions that we often get. And I was hoping maybe you can share more insights there.
Yeah, it's a great question, Alexis. Just to start off for the siting process for nuclear reactor, there's a lot of environmental assessments that take place, a lot of investigation, very thorough analysis of exactly where reactor units can be sited. Investigation as to the body of water. Is it large enough to facilitate, the capacity of reactors that are going to be put on site? And then seismic assessments, I can go on and on, right? But the reason why we need water is because of 2 things, right? One reason is, water is used as a heat sink for the reactor, right? So in the process of creating electricity, the first reason is because the lake water is taken, it's filtered, it's demineralized, right? And it's converted into water that's used to create steam, to spin turbines and ultimately create electricity, right? So you need water for steam production. The second reason is because, the heat sink, right? So reactors, they produce, they're used to boil water, right? And then basically you need water to cool down the reactors as well, right? So they're not 100% efficient. So like similar to your laptop or your computer that you're using to watch this webinar, it's producing heat, right? Or even your cell phone, right? So the CPU processor on your cell phone, it's producing heat, right? And basically the heat exchange is happening, right, with the laptop fan spinning in your room, right? Your room, the air in your room is being used to cool down your reactor, exchange that heat. So similarly, water is needed as a medium to exchange heat and operate the reactor effectively. So it's important to know that the waste heat that's produced, it doesn't negatively harm the environment, right? There's a lot of investigation that takes place to make sure that the body of water is large enough, right? The Ministry of Environment also looks into, the temperature differences and the outflow of the water as well. So those are important aspects that are investigated. So doesn't harm wildlife to any means. So that's kind of like an overview.
Yeah, I know. I was going to say, I know that for our project, because we're at the early stages and we've identified these potential study areas, that right now we're actually doing some studies to understand what the thermal impacts. So we're doing some modeling based on that, our SMR, because our water bodies are smaller than in Ontario, where Darlington, for example, is on Lake Ontario, which is a really big body of water. When that warmer water returns after it's cooled the reactor, it just sort of flows through the lake, and the temperature gradient change is insignificant. So we're actually doing thermal studies right now to understand what the potential impacts could be for the water bodies that we're considering here in the province. So yeah.
Yeah, I can add a little bit more too, just going back to our earlier discussion on that, steam through the turbine spinning the generator. And so typically what happens is that steam, after it comes out of the turbine, it's still fairly hot and it's also steam. And so a lot of the cooling you need is to convert that steam back into liquid cooled water to then send back to your boiler. And so whether you're a coal plant, a gas plant, or a nuclear plant, you need to condense that steam so you can cycle it back into your boiler system. And that's why a 300 megawatt SMR will need about the same amount of cooling as a 300 megawatt coal plant, because they're both trying to condense that steam back and send it back to the boiler system.
Yeah.
I think the coal needs a little bit less because a lot of heat comes out of the stack, whereas a nuclear plant has no emissions. And so a coal and gas plant will emit heat into the atmosphere as well as heat into the water, whereas there's no emissions from the nuclear plant. And so you have to get rid of all that heat through that heat exchanger.
Yeah, we just got a question around, speaking of coal, Boundary Dam, which is in southeast Saskatchewan, near Estevan. The question was whether or not it would be large enough to accommodate 2 SMRs. And so that is something that we are looking at, because as we narrow down to a site, we're looking for a half section of land here in the province. And we're making a decision in 2029 on the construction of 1 SMR, but that half section of land, we'll move it through the licensing process and the regulatory process to potentially host 2 in time. If the decision to move forward on SMRs continue in the province, and if that first decision is a yes in 2029. So now is the water body in Boundary Dam large enough to support 2 SMRs? We would expect, right now, it was chosen because it could support up to 2 SMRs. All of the water bodies were chosen in that way. But as we continue to do more studies on that water and on that volume of water and what, again, those thermal impacts could be, it'll help us understand the differences between one of those lakes versus another. So. Another question. So about closed and open systems for water. So could maybe Steve or Osama maybe explain a little bit about the idea of closed water for the reactor, for the turbines,
that's
that
right.
steam production,
that's
and
right.
then open for cooling?
I think I get what the question is around. So yeah, so the water that's going through the reactor and then is becoming the steam and then is being condensed and going back to the reactor, that is what we would call a closed loop. So that water is in the reactor almost for the lifetime of the reactor. It doesn't interact with the environment at all. It's a sealed system, kind of like the radiator in your car. It's a fixed amount of liquid, and it flows around and it does its cooling. And for us, it's doing the turbine stuff, and it never goes out into the environment. And then the open loop is the water you're pulling from your body of water to cool that steam down through some kind of condenser or heat exchanger, and then sending it back to the body of water. So the reactor or the coal plant or the natural gas plant isn't consuming water from the body. It's just pulling some in to do some cooling and then sending it straight back. And so that's an open loop system. And then the cooling part is a closed loop for reactors. I think some of the coal plants, as I just saw when I drove down to Estevan recently, there's a lot of steam coming out of Boundary Dam, and that's because they do blow some of that steam off because they don't have to have a closed system like a reactor does. And so you won't have these huge, you don't see steam. Maybe Osama can confirm. I don't think there's large steam plumes coming off the nuclear reactors in Ontario like you see at the coal plant. And that's because the cooling system is closed in a nuclear reactor.
Okay. Yeah, are there cooling stacks in Ontario on the nuclear facilities?
No, so those cool looking big towers, you don't see those in Canada. The reason why is, like Steve said, like our bodies of water are so large that we don't need cooling towers. But if you drive down to the States, you'll see a lot of those.
Right. And I think the CANDU is a little bit different too, right? That it might not, or maybe I'm wrong on that it might not need cooling towers in the same way, or?
No, I think it relies on the huge lake. So it's just a massive amount of water. So technically cooling towers could be an option in Saskatchewan, but it's a significant cost to go down that route. And so if you have a large body of water that can support the system, then that's typically the way that's done. That's why most reactors you'd find on coasts or large bodies of water. And then where that's not an option, you'll see the cooling towers. Okay.
We've got lots of really good questions flowing through. Just one on, I know we were talking about enrichment facilities just on the last slide there, but just do either of you know if there are any plans to develop enrichment facilities in Canada for long-term sustainability and stability? Because I know Ontario Power Generation is looking to build the first SMR, the first GE Hitachi there on their Darlington site. Having it operation. I think Osama, was it 2028 is the target date for that project? Yeah. And so any insights on the enrichment plans? I know that's probably a national conversation.
That's right. It very much is. So there's no short-term plans. No one's submitted to the CNSC that they have plans to build an enrichment plant. There's nothing like that happening in Canada today. But there are some thoughts in the long term. As a country, we move towards enriched fuel, and is enrichment something that should be considered? And so it is possible under our rules and regulations that you could enrich in Canada, but there's a lot of complications and it's a significant investment to do it. And as of today, Canada doesn't need enriched uranium for our energy needs, but that may not be the case in 20 years time, depending on how these SMRs roll out. And that's definitely going to be part of the conversation going forwards.
Interesting. Okay. I just wanted to touch on something else that comes up often around the idea of radiation. So thinking about that a little bit more and just trying to change my slides. What is radiation? Who wants to field that one?
Sure. And I should clarify too. When you say radiation, that can also be if you're standing around a campfire and you feel the heat on your face, that's infrared radiation coming off the campfire onto you and is transmitting energy in that way. And so when people talk radiation in the nuclear context, we're typically talking about ionizing radiation, which is a little bit different. And so those fission reactions that I talked about that created those little fission products that we saw in the video, those things are radioactive and will emit ionizing radiation, which can be either different types of particles, things called alpha particles or electrons, or it's X-rays or gamma rays. And so that's what you would get if you go, to the dentist office and you get an X-ray. That's a form of ionizing radiation, which can also be generated by spent fuel. Or if you look up, you're getting cosmic radiation raining down on us all the time from space. And so it does also exist in nature as well as what gets created in a nuclear reactor. I think we can talk about this for a bit. I think Osama might have a few bits to add.
Sure. Yeah, radiation is really, really cool phenomena. And like Steve said, like it's naturally occurring, right? So two major sources of radiation. One is kind of from outer space, right? So from our sun, and luckily for us, we've got our atmosphere to basically protect us from that, right? But when you're on a plane, right, you see the middle picture right there. You actually get a considerable dose, right, of radiation while you're in the plane. So, fun fact is a typical flight crew usually gets around 3 times the amount of radiation dose in an entire year as opposed to a nuclear worker, right? So, and the reason why is because when you're in that plane, you don't have as many, you don't have the atmosphere, the different layers of atmosphere kind of protecting you from that, from solar radiation. There's also places, in the world that have a very high level of background radiation, right? Like there's a city in India, Kerala, or another city in Iran, Ramsar. So there's a few locations across the world which their soils are so radioactive, right, that they have a background radiation dose, background radiation of around 250 times that of like the average across the world, right? So yeah, it's really cool. It's cool and interesting because that it's out there in nature, right? So yeah.
Right. And I often think, I know, Steve, you talked a lot about bananas, or
right.
I don't know.
I see
Steve,
the banana there in the picture. No,
I mean, I don't know. I feel like also, Osama, I don't know if you have any thoughts on why the banana is alongside the flight and our dental X-ray too. But if someone wants to kind of explain why that's on my slide.
That's right, for sure. So there's a thing, again, an isotope. Remember we talked about uranium-235, uranium-238 as isotopes. There's an isotope of potassium, potassium-40, that exists in nature. And you may know that bananas are healthy for you because they're a great source of potassium, but that also means they carry some of that radioactive isotope. And so there is a tiny amount of radiation dose that you get by eating a banana. But it is incredibly small. I mean, we have the ability these days, we have such great technology that we can actually measure it and quantify it. And so there is technically an amount of dose there. And so often that's used to qualify, how many bananas is an X-ray or something like that. And it's just a way of putting radiation dose into context.
Okay. So when I think about going to the dentist and ways that they protect us from that X-ray experience, remember, they usually put that heavy, I don't know if it's like a lead apron, like they put that apron on you, right? That essentially protects your body. But what is it made of? Lead? Like, what is it made of? And what is it doing?
I think it most likely is lead. And so I talked about gamma rays as one of the types of ionizing radiation. It's also X-rays that you're getting at the dentist's office. And so that lead is literally blocking that radiation from going through. And so they place it on you to protect sensitive organs while you get your X-ray of another spot. And so when it comes to radiation shielding, it becomes a bit of an engineering challenge to figure out the best way to do it, because the X-ray technician could technically give you a large block of concrete and it would also shield you, but it's not a practical solution. And so it depends on what the material is, and then we figure out the best way to provide that shielding. And so in the dentist's office, that little sheet is good enough for you, but then you'll probably notice that the operator will leave the room. And so their shielding is just by not being present. And so that's another way you can shield, is just with distance as well. And so then you'll see in the nuclear industry, all these different types of shielding are used. And so I know, for example, the spent fuel is shielded by a lot of thick concrete. And part of that's also to do with cost, and that it would be very expensive to shield it all with lead. And concrete's a much safer material just to work with. And so often we'll use concrete for shielding in some instances.
Yeah, what are, Osama, I wonder if you can share more about some of the shielding that is built into nuclear facilities.
Sure. Yeah, I think like Steve mentioned, like concretes, right? Like we use a lot of concrete throughout our facilities. You may have seen some pictures of like those concrete dome like structures, right? And that's that's basically shielding, right? Another one is water, right? So water is a really good shielding mechanism that's used. If you may have seen those spent fuel bays where kind of spent fuels kind of stored, and you have thousands of these assemblies from the reactor, which is the waste product. But you can stand right on top of it very safely, right, without getting any dose or much dose at all, to be honest. And the reason why is because water is basically acting as a shielding mechanism, right? So there's a lot of different design requirements and materials that are used in the power plant. There's also PPE, right? We're always wearing protective equipment inside the power plant, right? So we've got different filters that also protect us from alpha radiation, which is a different type of radiation. We have plastic suits, so not all the time, right? So there's majority of the plant you can walk around in a t-shirt and kind of hard hat and kind of like regular safety equipment, but there are specialized areas where we have a little bit more protective equipment that's deployed as well.
Interesting. So yeah, go ahead, Steve.
Yeah, no, I was just going to add, and I know we talked about lead and concrete, but basically every material out there shields radiation to a different level. And so typically the more dense it is, the less of it you need. And so, for example, I talked about that cosmic radiation from space. Just the roof above your head will actually add quite a bit of shielding to that space radiation. And so typically if you're doing radiation measurements, you'll find a higher measurement when you step outside to inside because the building is shielding you from that cosmic radiation. And so everything shields to some degree. And then, lead is very great at it because it's so dense. But there are lots of different options.
Interesting. I want to sort of shift gears and talk about types of waste, because I know that this is a big question we get often. And during our webinar a couple of weeks ago, where we talked about nuclear waste, specifically spent fuel. And I think, Steve, just given your background in fuel research, can you explain the different types of waste that are generated from a nuclear power plant? I know we talk about low and medium and or intermediate and high.
That's right. And so low, I think like we see there, is kind of your clothing, rags, gloves. And so it's contaminated and it's slightly radioactive, but not enough that you need any kind of shielding, and there's no heat being generated from it. So it could also be, your smoke detector in your house might have some americium in it, and that is an example of a low-level waste. And so it still needs to be managed, but it doesn't pose a risk to you to be, it could be in the room with you and that would be fine. And then as you move up in the different levels, we're essentially talking about the amount of radioactivity and to a little bit the amount of heat as well. And so the intermediate level waste is now slightly more radioactive, but enough that you have to think about shielding when you store it, and so that it's not a hazard to people in the workplace. And so that can be equipment that's actually inside the reactor, can get activated and contaminated, or equipment you're using to purify contaminated liquids or something like that. And so there's not as much of that as you see of the low level. And it's something you have to then provide some kind of shielding, which in some instances can just be steel, like a steel barrel may or may not need extra shielding. Again, it depends on the intermediate level waste that you're putting in there. And then at the highest end, which is the high level waste, is that spent fuel coming from the reactors, which is highly radioactive. And so you do need significant shielding to protect people from those. And that can either be the spent fuel bays, which I think Osama talked about, the big pools of water that the fuel's sitting in, or these large concrete canisters that will shield you from that. And those ones will also generate some heat. And so you have to think about that as well.
We actually have a picture of that kind of coming up, those fuel fuel bays. But I just thinking, Osama, I know in the on the screen here we have a little bit around the amount of waste or the volume that's generated. Can you speak to that a little bit more around the amount of waste that is generated from nuclear power plants?
Yeah, sure. Just you'll see the percentage of volume there, and you'll be surprised by the amount of high level waste, which is kind of the spent fuel that's produced. A very small fraction of the other radioactive waste that are produced by a nuclear facility. But what's interesting is that the nuclear energy industry across the world does an exceptional job in like uh, tracking all of this waste, right? So the industry knows where every single gram is, right? And ultimately, we're the stewards, right, of this waste. We're responsible for management, and internationally, no one has ever died from the waste product, right? Or even when it comes to transportation of this waste, there haven't been any accidents because we take so many proactive measures in transportation containers, the types of trucks that we use. Yeah, I think the concept of waste, every energy source has its own type of waste, but I think when it comes to nuclear, that's actually one of the advantages, right? Like the amount of waste that's produced and how safely it's managed, as opposed to fossil fuel production, where that waste is going right into the atmosphere and not really managed well. So yeah, I think this is actually one of the advantages when it comes to nuclear energy waste. People are sometimes scared, but I think there's a lot of positives there.
Yeah, for sure. And just to touch on the visual of what the nuclear waste management facilities look like. I think this is from Ontario Power Generation, right? So Steve, you were talking about there might be some heat. I
That's
don't
right.
know, Osama, have you had a chance to tour these bays yet at OPG?
Yeah, I've had a chance to walk up to one of those containers and actually touch them as well. So there's spent fuel in there. It's completely safe to even be around those, right? Because you're shielded by the concrete in the containers. And as you can see, the individual there, he's not in a plastic suit, right? He doesn't have a crazy amount of shielding on him either, like a lead blanket like that you see with the dentist, right? So yeah, it was really cool time getting to experience that, seeing the spent fuel bay and other areas of nuclear waste, and seeing how safely it's kind of there. Yeah.
I was just going to say, one of the folks who are listening in just felt like it was a little bit unclear, or they want to understand a little bit more around how radioactive is the accumulation of nuclear waste from a reactor. So is it safe to be beside it, unshielded, or for an extended period of time? And what if you drank or ate it by mistake? So I know we've touched on that a little bit here, but I'm just curious if you can just touch or maybe explain a little bit more around whether, why is it unsafe when it's unshielded?
Right. Yeah, it is emitting a significant amount of radiation that if you were, it's definitely not recommended. But yeah, if you were to walk up to it and try and pick some up, you would get physical burns, radiation burns on you for sure. And you could find yourself in hospital, that kind of stuff. So it is an incredibly powerful source of radiation. And that's why we have all of this shielding methods in place. And that's why the fellow in the picture can stand there and touch that container, even though it's got highly radioactive fuel inside. And so we always have that shielding. And there are lots of processes and protocols in place in Canada to protect both the workers and the public from the radiation from that spent fuel. And I think part of it to keep in mind too is that there isn't a significant amount of it. So, it's this one building at OPG that stores all of its waste. And then for the SMRs, they actually do an even better job at the energy density. So the reactor that SaskPower is looking at, I think it's 3 or 4 times as much energy from the same pellet compared to a CANDU reactor in Ontario. And that's because of the enrichment that we talked about earlier. When you increase that enrichment, you can burn, we call it, the fuel much longer. But from a waste perspective, it means we end up with even less waste for the amount of energy that we've generated. And so, yeah, it is hazardous, and a lot of effort is definitely put into managing it and managing it safely. And I think Osama may have touched on like the transportation. And if you Google on YouTube, there are videos of testing of those transportation containers. including 2 tests where they park them on a railway track and specifically hit them with a train. And it's a neat video to watch. And the waste transport container completely destroys the train, and there's no release from the container.
Yeah, there was a question around, does nuclear waste storage ever leak? And I know in our conversation a few weeks ago around why we're thinking about nuclear, we described and confirmed, nuclear waste or spent fuel is actually a solid, right? It's not a liquid or a gas.
No.
So the idea of it leaking is sort of a different concept once you start thinking about it as it was described as tools in a toolbox, right? So this is your big toolbox, and if you were to dump it out, it'd be like your tools falling on the ground, so they wouldn't roll, they're heavy. Same with the fuel here. And I wonder, Osama, there's a question around how much waste will be produced over the operational life of a nuclear reactor, and how long will that waste stay radioactive? Any equivalencies top of mind for waste in Canada, or at least Ontario?
So for Canada, like the province that I live in, Ontario, like around more than 60% of the province runs on nuclear. And for the past 60 years, we've been we've had nuclear facilities that have been producing electricity, right? OPG specifically has been operating its reactor units for 50 years, right? Half a century, right? Pickering. So the amount of spent fuel that's been produced overall has been equivalent to 8 hockey rinks. 8 hockey rinks if you stack the fuel from the bottom of the rink to the boards, which is actually not a lot, right? In that amount of time. So your lifetime worth of spent fuel can fit in the size of a soda can, right? So that's how much waste that's being produced. If you were to take an equivalency, if you were to see the fossil fuels or any other kind of energy source, you'd be very amazed to see how much waste is actually produced. So yeah, nuclear produces very less waste overall.
I was gonna add, those pellets are also a ceramic, which is a very stable material, and so it's a solid ceramic that they're stored at. And one of the last things I was doing before I left Chalk River Labs was an experiment that was started, I think, in like 1962, with some of the very first CANDU spent fuel. Came out of the very first CANDU type reactor, let's say. And so that fuel has been monitored for the past 60 years, and it still looks in great condition. It was kind of a bit boring from a scientist perspective that nothing had changed, but that's kind of what you want to see. And the facility where this fellow is standing, they'll also be monitoring all the time too, to see that there isn't any kind of escape, but they're these solid ceramic pellets. They're very robust.
Interesting. Yeah. And I'm just looking at time here. We have 5 minutes left. I didn't think we'd just plow through this material, but I do want to ensure that we get a chance to talk a little bit about safety and security, because I know that's really an important aspect of all nuclear facilities. And I was hoping that maybe Steve, we'll start with you. Just
Sure.
Very quickly, in like about a minute, what are some of the enhanced features with SMRs specifically? And then we'll talk about the nuclear. We'll give you a minute too, Osama, to talk about
That's right. Yeah. So a lot of the SMRs, which you also see with the GE Hitachi one, South Power, they do a lot more what we call passive safety or natural safety. And so it's more about using things like natural convection to provide cooling and flow in the reactor, whereas traditional nuclear power plants like the CANDUs will use mechanical pumps. And so if you have pumps, you need electricity to drive pumps, you need backup power to drive those, you need emergency backups for your backups, and you need a lot of these features to make sure those pumps run. Whereas the SMR that SAS Power is considering, its main flow through its reactor is driven entirely by natural convection. And so it creates a very different kind of accident scenario case where you don't have any pumps in the first place. And so if you lose power, the flow will continue because it's not driven by power, if that makes sense.
Interesting.
And so it's this very passive inherent safety or safety by physics approach. And they can do that because they're smaller. And so you can get away with these kind of very cool engineering tricks.
Right. And the onion on the screen is meant to depict the idea that in the nuclear industry, there are layers of protection. Yes. Osama, I often, because we're talking to people in Saskatchewan about what are some ways that people living within a nuclear facility are protected. Are you able to share a little bit more around the communities living close to the facilities in Ontario? How are they, what are some ways that their risks are managed or protected if something were to happen at the plant?
Yeah, I think, when it comes to Pickering Nuclear Station, the station that I work close by, so there's neighborhoods right next door, right? So you know in the 50 years of operation of that station, no one from the public has been harmed, right, from the plant there. We actually have a really nice beach right next door, so you'll see a lot of folks going there. Yeah, like you said, Alexis, there's layers of safety, right, that that are basically there. It's called defense in depth, right? So basically, at a nuclear power reactor, you have the containment system, right, which is designed to lock in any radiation harm from the facility, right? You'll also see these containment systems have even tests with with jets flying into them and them being able to take that impact, right? Also, you have shutdown systems, right, in a nuclear power plant that stop the chain reaction within seconds. So overall, those are kind of like some of the systems that I can cover quickly. So yeah.
Yes, sorry this is the worst part of today's conversation to sort of rush over, and maybe if we can just run a little bit longer. I don't know if either of you have 5 minutes to spare, but I often think about some of the natural disasters. Like if we think about Fukushima and the tsunami that occurred there, and some of the potential extreme weather events that could impact facilities because of climate change, like increased extreme weather events and frequency of those. What are some kinds of protections that we have in place for these extreme weather events that we can anticipate in our areas, our regions?
Yeah, and so some of that leans towards some of that inherent safety that I was talking about. So the Fukushima reactor was a boiling water reactor, which is the same as the SMR that SaskPower is looking at. But one of the key differences is that large reactor had kind of active cooling. And so what I didn't mention when I talked about fission, and you have those fission products, they continue to generate heat even after the reactor shuts down. And so when you shut a reactor down, you still have to provide cooling. And so those large power plants, that cooling is provided through mechanical means. And so you have large pumps, you have backup pumps, and then you have generators and you have backup generators. And then usually we're talking about the onion, your final line of defense is to drive generators in from offsite. And so in Fukushima, that layer failed as well because they hadn't anticipated, the country being destroyed around the reactor. And so they couldn't bring that power to the site. Whereas for the SMRs, because they operate more on natural convection and passive systems, the operators at the facility don't have to actually do anything in one of those emergencies. So if there is a complete power outage or some weather event completely isolates the entire reactor facility for some reason, it doesn't actually need power to keep itself safe. So it'll just naturally cool itself, and it's all based on natural convection processes. And it can do that because it's a much smaller reactor. They're 300 megawatts, whereas the Fukushima one was 1200 or 1600. And so that makes a big difference. And that's why these SMRs can deploy these inherent passive safety features that really allow it to kind of hang out in a safe state without any operator interaction, and it doesn't need any offsite power. Whereas these larger reactors do. And so then they have a lot more defense and depth to protect against that.
Right, and Osama kind of touched on a few of those. And so just thinking a little bit more about, I know we have another question here around, we're totally going over time. We went over time last week too, hey? Like 20 minutes over time. I should have prepared folks. There was just one quick question. I know we missed a few here, but how do we connect SMRs to the existing grid? And I should probably know that first and foremost as the SaskPower representative, but we'll follow up on that question after today's chat, just because we're kind of running out of time. But just really quickly, I think there was another question that I may have missed at the front end, tied to so we talked a little bit about the enhanced safety features with SMRs and about uranium-235. So if uranium-235 is enriched, so this is not tied to the safety and security, is there spent uranium, was the question.
As in the spent fuel? Yeah, there is both uranium-235 and uranium-238 in the spent fuel. But if you start at 4 or 5%, like is being thought about for the SMR for SaskPower, when it comes out of the reactor, it'll actually be about 0.9% enriched in uranium-235. So in fact, the spent fuel from the SaskPower SMR is actually technically enriched when it's sitting there and it's considered waste and spent fuel. It's about 0.9% uranium-235, whereas the stuff in the Athabasca Basin is 0.7%. And so there still is uranium. Most of that spent fuel in those
higher
canisters.
than when it would naturally come out of the ground.
Oh yes.
Yeah.
For the SMRs, it's still a bit higher than what comes out of the ground. That's why there are some advanced reactors that are looking at using that spent fuel as their source of fuel because it does contain uranium.
Right. Okay.
Yeah.
Okay, so we will probably pause it there, I think, but they were all really great questions, and for those that we didn't get to, we'll make sure to follow up. With this being our last of the 5 online learnings sessions, we're going to be doing a report back and providing information and answers to all the questions that we received over all of these conversations. And just one final note that I want to leave folks with is to share that we actually have a virtual open house for the project coming up on December 7th. So we're holding one from noon to 2 p.m. in the afternoon, and then in the evening from 7 to 9. And think of it as sort of like a open door chat, some presentations, choose your own adventure. We'll have a number of industry experts joining us. Some of your colleagues, Osama, will be popping in from Ontario Power Generation. We've got some of our representatives from, I think the Nuclear Waste Management Organization is hoping to be there. We'll even have representatives from communities who live in and around the existing sites in Ontario as well, to share about what it is like to live close to a nuclear facility. Although Osama, it was lovely to hear that there's recreation right next door at a beach near Pickering, and enjoyed by many. Also want to remind you that we have a few online engagement tools. We have our engagement hub at saskpower.com/engage, where you can share more information around your questions and ideas around our future power planning, including our nuclear project, our SMR project. And then we also have a generation dashboard. I know at OPG, you guys have had a live generation dashboard where people can kind of see where their power is coming from at any one time. And we too have recently launched something similar where people can kind of see how much power is being generated by the different supply options that we have on our grid today. So it's exciting for us to finally launch something similar. So go check that out as well. And so with that, I just want to thank everyone again for taking the time to join us during your lunch hour today. I hope you learned something new. And thank you again to Steve and Osama for taking the time to share a little bit more about how nuclear works. Really appreciate your time.
Yeah, thanks.
Thank you so
Great
much.
conversation.
Okay, great.
Yeah, see you guys.
Bye.
Bye.